So let me begin by thanking all of you for being here and thanking the organizers for this invitation. This is the third one of these conferences I've been to, and it's always a pleasure. It's just wonderful to see that, thanks in large part to the Fetzer Franklin Fund, there are now conferences taking a serious approach to such forward-thinking questions, and it's really an honor to be speaking in such august company, so I hope that I can do it justice. As Basil already mentioned, I spoke a little bit at the previous conference about surrealistic quantum trajectories. Now I want to take a step back from surrealism and talk about neoclassicism. So I hope that'll start to make sense to you as we move on. There are really three things that I'd like to do. First, I'm going to recap an experiment that we completed about 2 years ago, and it was a long project, but I have new things to say about how we now think about the experiment and some open questions about what I think it tells us about the quantum ontology. In particular, I want to spend a lot of time comparing with this neoclassical theory, which was an idea due to Ed Jaynes. Some of the people who know old-fashioned quantum optics in the audience may know what I'm referring to. For the rest, I'll try to explain it. But the deep question to me is, what should we learn from weak values, from the weak measurement experiments that I'm telling you about? What do they tell us about a possible ontological theory that underlies quantum mechanics? Since that, of course, is the focus of this series of conferences. In particular, I'll think about a theory in which the electromagnetic field has definite values. Not that I'm espousing such a theory, but I want to think about the similarities and differences between that theory's predictions and what we get in our experiment and what you get from weak values. And I think, hopefully, that provides a little bit of a signpost pointing us ahead. There are a number of other experiments that I wish I had enough time to tell you about in detail, but on the other hand, they're still underway, and I prefer to be able to show you the results of the existing experiments. I'll just try to advertise these other three experiments at the end. One, looking back at Bohmian trajectories, but now contrasting trajectories in momentum space with the ones we previously observed in real space. Looking at this pigeonhole paradox many of you know about, but what it tells us about some rules and other rules about what I'll call weak-valued probabilities, and hopefully an update on our long-standing experiment to measure the tunneling time of atoms using weak measurement. Before I dive into that material, I want to give proper thanks to the people who've really done the work I'm going to be telling you about, and it's a long list over the years. The experiment that I'll describe, looking at counting a single photon and getting a result of 1,000, that grew out of a project that was really led by Amir Feyzpour and Greg Dmychowski, and later picked up by Matin Halaji, who was the first author on this most recent version, and is now being run by Josiah Sinclair with a few other people who've just joined the group. The photon weak measurement experiments we've been doing for a long time, notably with Kevin Resch and Jeff Lundin, who've gone on to do exciting work in the same directions. The ones I'll talk about now are being worked on by Noah Lupu-Gladstein and Arthur Peng, supervised by my more senior students, Ugo Ferretti and Edwin Tham. In addition, we've got two postdocs who've been instrumental in all this work on the experimental side, Kent Bonsma-Fisher, and for all of the weak measurement theory support, Aaron Brodich. Now, to tell you what I mean by counting a single photon and getting a result of 1,000, I'm going to have to go back to basics. So I want to tell you how we're going to count photons at all. So the first part of the talk is on how to count a single photon and get a result of 1. And the original motivation for this experiment was not foundations. This is actually something we began working on for very practical reasons. We want to open up a new field of optical physics, a field of quantum nonlinear optics, which could have important applications to quantum information processing, but I think fundamentally is just the frontier of optical science now. We want two photons to interact in a way that this cartoon tries to depict, so that as one photon propagates along, a second photon can tell it where to go, tell it whether or not to be transmitted in the simplest sense. How do atomic physicists like to do this sort of thing? There's a standard kind of scheme. There are a few, but this is perhaps one of the simplest. It's something known as cross-phase modulation, where I'm not going to try to switch the direction of a second beam. I'm going to try to modulate its phase and use that as a measure of how many photons are present. So we imagine that we have some atom here, its energy levels, and there's a probe that's on resonance for now with one of these transitions. And now I send in another photon, some kind of a signal pulse that I would like to detect. The idea is that that signal pulse affects the state of the atom. It writes what's known as an AC Stark shift, shifting these levels to the dashed lines. And that changes the detuning of the probe from its resonance. So if you look at this resonant feature on the right, if that begins to shift, Suddenly the probe is off resonance, it sees a different index of refraction, and it picks up a modified phase shift. It turns out that phase shift is proportional to the intensity of this signal, or in quantum language, to the number of photons. And in fact, if you write out the full quantum treatment, it is strictly proportional to the number of photons in that mode. So we can think of this phase shift on that transmitted probe as a way of counting the number of photons. That's the basic idea. How do you make that strong enough that you could see a single photon instead of 10 billion photons as in the more classical experiments? Well, there are a number of answers, and I won't even tell you about the most modern ones involving Rydberg atoms. Some of them use a technique known as electromagnetically induced transparency. And again, the quantum optics people know what I mean. For the rest of you, it doesn't matter. It's a technical detail for now. It leads to a level scheme that looks like this. The experiment involves beginning with a cloud of ultra-cold rubidium atoms, laser-cooled to a few microkelvin, adding an extra beam here indicated in blue that you can think of as a catalyst. It just sets up the situation where we have these very large phase shifts. Then a signal pulse, hopefully one photon, focused down through the atoms. And in our case, in the opposite direction, a probe beam also focused through the atoms, which is then detected in a complicated manner that lets us look at that phase. And hopefully this phase we measure will tell us how many photons were in the signal beam. Now, our original plan, and still our longer-term plan, is to send one photon at a time in through a source that we've developed in Toronto. At the moment, the source isn't bright enough for us to do that. So I'm going to tell you about what we did instead, which, as is often the case with Plan B, I think proved to be much more interesting than Plan A. Here's the classical measurement. As we change the average number of photons per input pulse, and I say average because these are now classical beams. They have Poisson statistics. In other words, each photon is independent from all the others. As we turn that down, the phase shift that we measure goes down. But by the time we end up with only one photon per pulse, we have about a 15 microradian phase shift, and we're able to measure that. Not on a single shot, for those of you who care about the applications, but on average. And this was already the first experiment where in free space, the nonlinear phase shift written by a single photon level pulse had been measured. So we were excited enough about that. And we started really looking at what happens if we send in 5 photons. There's the measured phase shift. What if we only send in 2 photons? Naturally, we were about to send in 1 photon when it occurred to me, why stop there? We're looking at classical pulses. We don't have to quantize them. I could send in half a photon. What would happen if I sent in half a photon? Well, if you think about it, you realize a half photon coherent state just means something probabilistic. It means that roughly half the time there's no photon, and roughly half the time there is a photon. The nice thing in our experiment is these atoms are essentially transparent to those signal pulses. So I could let that pulse propagate through the atoms and then send it to a detector. And when I send it to that detector, if it clicks, I say, oh, that was one of the cases with a photon. If it doesn't click, and if I had 100% efficient detectors, but we'll sweep that under the rug for now, then I say, oh, there wasn't a photon. And we can compare those cases. So experimentally, when we sent in half a photon, there's what we saw. When the detector did not fire, on average, we saw no phase shift. When it did, we saw that 13 or 15 microradians. So there was really a measurement of the phase shift due to a single photon. And we spent some time thinking about it. I mean, if we have this classical pulse that has an uncertain number of photons, and then there's a click, what do we really say about the photon number? And we made an interesting discovery. And I won't lead you through the derivation. Here are 2 cartoons, but the conclusion is that after a detector fires, what you should predict, or retrodict, about how many photons were in some region, is exactly what you expected before the detector fired plus 1. And if you just go through the calculation, either, frankly, classical Bayesian statistics works fine. My students weren't as confident. They did a really complicated quantum mechanical calculation. I told them it would give the same result. It does. There's the result. If you know a fair amount about quantum optics, you could also just look at this picture, and then you'll hit yourself in the forehead and say, oh, it was obvious all along. It really is obvious all along if you think the right way. But it raises the following question. When that detector fires, and I conclude, oh, now, in addition to all the stuff that I wasn't seeing, there's one extra photon. Is that the photon which made the detector fire? That's my natural tendency. I feel like, in addition to what was going on in the background, the fact that this detector fires means there's the photon that got to that detector. And we can start asking what it did. Obviously, that's dangerous language. You should either not use it, or at least be careful with it, or do what I'm doing and apologize for it after the fact. But those are the natural questions that I think it leads. And experimentally, this is what we see. For every one of those input states, we could compare the cases when the detector did not fire and those when it did. And in every one, we see this extra 15 microradians or so. So while the first experiment required a calibration, you had to trust me when I said, really, that particular intensity corresponded to an average of 1 photon per pulse. Here, you don't have to trust me. It's nature telling you there was a click, there was not a click. It's really 1 quantum difference. So this is a no calibration required measurement of the nonlinearity due to a single photon. Well, now we can get up to part 2 of part 1. Can we ask what that photon was doing before it went click? Now that I can say the detector was triggered by something in that interaction regime, can I figure out what was going on before we observed it? How do we describe, in other words, post-selected states? So this is where we get into weak measurement, and I don't have time to do an entire primer on weak measurement. To some of you, it's already familiar, but for the rest, let me try to get the bare bones across. The idea is that I'd like to know if I have some system, some wave function we've indicated schematically here, and it interacts with some measuring apparatus, but then I post-select. I make an observation later, like this detector goes click. What should I be able to say about the behavior before that post-selection? Well, the only way we can really define such a thing operationally is to ask, what would the effect of the system have been on the pointer? The normal objection is to say, well, if you put a measurement interaction here, you introduce what Bohr called an uncontrollable, irreversible disturbance, you can no longer talk about the evolution to this post-selected state. And the solution, due to Aharonov, Albert, and Weidmann, is to say, what if we just tickle it very gently? What if we do our best not to disturb the system too much? So we'll make a weak measurement here, and we'll see on average what that does. So this is what the scheme looks like. To make the measurement not very disruptive, one way you can think about it is you use a pointer with a very large initial uncertainty. Turns out that large uncertainty leads to very small uncertainty in the degree of freedom that gives you the back action, gives you the disturbance. So the wave function interacts with the pointer. Sometimes the post-selection succeeds, sometimes it doesn't. If it succeeds, we look at where the pointer is, and we get a random position somewhere in or near that distribution. We don't learn very much from that, but we repeat this millions of times, and we keep only the pointers that correspond to successful post-selections. We throw out the others. And we accumulate a distribution of pointer positions. We can draw a sort of histogram. Where does the pointer show up? And we ask, where is the peak of that histogram? Where is the average pointer position at the end? And this can all be modeled by straightforward standard textbook quantum mechanics. But if you do that, and you work out that position, this is the result you get. If you're measuring some observable A, the answer is not the expectation value of A, it's A sandwiched between the initial and final states and divided by this overlap. This is the weak value formula. And it has many interesting properties, as first pointed out in the famous AAV paper, how the result of a measurement of a component of a spin 1/2 particle can turn out to be 100. Obviously the inspiration for the experiment I'm telling you about. This quantity can be arbitrarily large. If you make the overlap between initial and final states very small, you can get an arbitrarily large weak value. Now, of course, that overlap governs the success probability of the post-selection. So you have this trade-off, but that's no reason not to do it. I'll point out that it was proposed that this might be useful in practice. It's an effect known as weak value amplification. It's pioneered first by Hostin and Kwiat experimentally, and then by John Howell and Andrew Jordan in terms of really characterizing it. We now have a new paper on the archive just accepted for publication where we try to summarize under what situations we think this is useful for real-world applications. But today I'm not telling you about the real world, I'm telling you about quantum ontology, so let's just move on. This is going to be our application of that to the measurement of the number of one photon. So instead of sending one photon through our atom cloud, this thing I've labeled interaction over here, imagine that I send a photon into an interferometer where the photon could either go through the cloud, path B, or miss the cloud entirely in path A. Well, then I've prepared the photon in a state, let's say A minus B over root 2, for the sake of argument. Now, how am I going to do a post-selection? Well, I'll combine these two paths at a beam splitter, and if a detector fires at this port, that's projecting onto a particular superposition of A and B. And if we tune these two reflectivities to be almost equal but not quite, then this port will be very dark. Very few photons will land there, but some will. That means the overlap between f and I is small. So mathematically, f is Ra plus Tb, but we'll let r and t be 1 over root 2 plus or minus some delta. Now let's ask what it would mean to count the number of photons in path B, because that's what our nonlinearity, our Kerr interaction, is supposed to be doing. Well, it essentially means we're measuring the projector onto B. That's what represents the photon number in B in this case. And if you work it out, the important thing is just that this denominator depends on that small delta. As delta goes to 0, the denominator goes to 0. So the number of photons seems to diverge as 1 over delta. What that means physically is that when the post-selection succeeds, when this detector fires, you should expect that the mean phase shift on the probe will be much larger than it would have been for a single photon, even if you sent in strictly 1 photon at the input. Remember, I admitted we're not doing that yet. We're working our way there. But we're going to talk about the effect of that 1 post-selected photon instead. So this was theory that came out in 2011. The experiment just came out earlier this year. I'm now going to shift gears a little bit, and this is mostly to make Lev happy, and I hope it works because usually I make Lev angry. I want to point out that there's a difference between this experiment and earlier weak measurement experiments. Most weak measurement experiments, including my own, used optics, but they used multiple degrees of freedom of the same photon. Something that you wanted to measure, perhaps the polarization, and then you would use the position as a pointer, or in some cases the other way around. This experiment is the first work that uses deterministic entanglement of 2 different optical beams, a real interaction between one beam and another one, so that there's one system and something completely separate that serves as the pointer, the measuring apparatus. Let me show you why this is important to me. This is what the experiments look like that used, let's say, position as a pointer. If we wanted to measure weakly whether or not a particle was in a given path, we would do something like stick a piece of glass in that path and cant it off a little bit from the vertical so that any photons that went through would be displaced very slightly. Not too much compared to the width of the beam, the uncertainty in the photon position, but just enough that we could measure it after averaging over many trials. This was used, for instance, in our experiment on the 3-box problem, and I just want to point out this is one of these fascinating weak measurement paradoxes. It's a case where if you prepare a particle in the right superposition of 3 boxes and post-select it in the right superposition, and you ask, what are the odds that it was in 1? Or more strictly, what is the weak value of the projection operator onto region A? You get an answer of 100%. And if you ask what are the odds, weakly speaking, of it being in box B, you also get 100%. And in a recent experiment by Okamoto and Takeuchi, it was shown that you could use this to implement a kind of quantum shutter, where a single shutter could reflect a particle whether it went to slit A or slit B, or in fact any superposition thereof. In our earlier experiment, where we did this weakly, we used that position shift. And what we found is as we changed the measurement coupling strength and looked at how much the photons shifted, it didn't matter whether we shifted rail A only or rail B only. When we looked at the post-selected photons, they followed this 45-degree line, at least there exists a coordinate system in which that's 45 degrees, meaning that the shift for the post-selected photon was just as great as if all the photons had been going through path A, yet also just as great as if all the photons had been going through path B. Now, obviously that should concern you, because if the probability of A and the probability of B are both 1, how do you resolve that? It turns out there are a lot of strange features of these weak values. And in this case, if you ask about the probability to be in box C, well, it's 1 minus PA minus PB, so it's minus 1. And in the weak regime, that really is the prediction. We did that experiment by performing a weak measurement on rail C, and we could post-select either A, in which case C shouldn't move at all, or B, in which case it shouldn't move at all, or C, which is a calibration, it should move by 1 unit, or the important post-selection, and we'll see what happens. The A and B are the central curves. You see it doesn't shift. C shifts to the right because that's the direction that we had the slide inserted. But if you post-select on A plus B minus C, you really see the pointer shifts in the opposite direction. And that's all a negative weak value means, that the shift on the pointer will be the opposite of what you would expect based on the way it was set up. Now, I go through all of that because I actually want to show you how the experiment was done. This was just using single photons sent through a 3-path interferometer We could choose in which interferometer to displace the beam. But the post-selection involved looking at a screen that looked at a combination of A plus B minus C. From a classical optics perspective, because we don't need quantum mechanics to model this situation, we're just looking at interference of A and B in phase with a 180-degree phase shift for spot C. Now, think about the interference. What happens if I shift the beam in A? Suddenly, at the output, I have 3 spots, but B and C are perfectly overlapped and out of phase. They interfere destructively. All I'm left with is A. So if I shifted A by 1 millimeter, the output shifts by 1 millimeter. It looks like the photons all came from A. On the other hand, if I shifted B by 1 millimeter, A and C would remain perfectly overlapped and interfere destructively. The output spot shifts by 1 millimeter, as though all the photons had been in path B. Now, obviously, if you're just doing classical electromagnetism, we don't think there's any sense in which every photon I see out here really was in B and really was in A. This is just some effect of the interference. And that's why I'd like to get away from having the particle carry its own measurement pointer in this way. I don't want there to be this kind of trivial explanation. I'd like to let 2 systems interact and really be able to think of one as an external measurement of the first. Now, mathematically, I'll say weak measurement always boils down to this, right? It will always look like this kind of interference, but it will be in some much higher dimensional space that includes the degrees of freedom of the pointer as well as of the system. So finally, I think we can get on to our experiment about how a photon in the detector is worth 1,000 in the atom chamber. The first trick to doing this, a very useful trick for experimentalists, if you want numbers to be big, count in binary instead of in decimal. So our photon in our detector turned out to be worth 8 in the vacuum chamber, but it looks better in binary. And the experiment is not so different from where we started. We have this atom cloud, we have the 2 beams going back and forth, but now we want this interferometer for the signal, where it could either go through the cloud or not. Experimentally, it turns out to be much more clever to build up something where you use 2 different polarizations of the signal and choose an atomic level scheme where one of them interacts strongly with the probe and the other one almost not at all. We'll neglect that little correction. And that's what we were able to do here. So we send in light that's a superposition of 2 polarizations. We can rotate a polarizer here to pick out a different superposition. And we choose one that's almost but not quite orthogonal to that. And here's what we get. As we change that overlap, that delta, we indeed see down here is where the single photon phase shift would be, and we get the phase shift growing and growing and growing as we turn delta down until we got it to be about 8 times the single photon phase shift before we couldn't go any further without saturating due to some background issues. All right, so that really means that when you post-select this photon in the right way, the average shift on the pointer is larger than it could ever have been for just a single photon. And that's the mystery that we've spent a lot of time thinking about since then. Here's the question. Should we really say this weak measurement is the best way we have to ask what was going on between the preparation and the post-selection? And therefore, I should really believe that there were 8 photons on average in this photon, even if I only sent 1 in? Or should I just dismiss it as some funny interference effect like those classical spots? I think the answer is somewhere in between, but I don't like the idea that we should just say, no, this answer is too weird, it must not mean anything. Who would be the arbiter of which measurements are telling us about reality and which measurements are not? Right? At the end of the day, the way we construct our theories is to explain our measurements. And if we make measurements of a system between a preparation and a post-selection and they give us some result, our job is to figure out what are we learning about reality through that measurement, not to say that sort of measurement isn't telling us about reality. So here's one model that we started thinking about. Again, just as a toy model to explore this. It actually grew out of arguments with a referee. Should we think about there being more photons present, or maybe at least think that there's a field, some kind of classical field, which is larger than the single photon average when there's a post-selection? And I'll show you what I had in mind. It goes back to this quantum optics history. Sorry, but I wanted to remind you of one caveat I forgot to say. We're still using weak pulses that have on average 1 photon. And the thing that we're amplifying is only that post-selected part. All right, we may come back and relax that later. Yeah, that's right. It's a coherent state. So here's what my mind went back to, an old debate from 1967. This is Ed Janes talking to Peter Franken. And Ed Janes had shown that you could understand a lot of what's considered to be the quantum theory of light by using the old semi-classical theory, where light was treated as a classical field, but adding certain hypotheses. And it was a complicated debate, but let me boil the important addition down to the following. We know that there seem to be fluctuations in the universe. Instead of assuming that uncertainty, those vacuum fluctuations, come from quantization of the field, if you just make that a new postulate of the theory, the world is permeated by a random fluctuating electromagnetic field, that goes a long way to reproducing the predictions of quantum mechanics. And Peter Franken didn't think it went all the way. In particular, he thought that Janes wouldn't be able to calculate the value of the Lamb shift. Janes thought maybe he could, and they had a bet that lasted about 10 years. It's an interesting story. I was looking for this photo, and I found it in a book by Carlos Stroud, where he actually explains that the $100 bet, the idea was that Lamb would be responsible for deciding who had won, and he would invest those $100 in 1967 in Xerox, which was a wonderful idea. Being a physicist, he forgot to actually do it. So apparently Franken would have been a very wealthy man by 1977 had Lamb had a better memory. Anyway, the idea here is we did this calculation where we began with an initial coherent state, this Poisson distribution fluctuations in the field, 1 unit of vacuum noise, so to speak. And if you didn't start with that state, if you had a very noisy source, it turns out our original experiment wouldn't have worked the same way. When I saw a click, I would have been right to say, I'm seeing a click. Maybe this is one of those moments when my source is brighter than average. And in fact, in a very classical sense, you'd find that by post-selecting on the clicks, you biased yourself towards the brighter moments of your source. And that would explain why you get an extra phase shift whenever your detector fires. The interesting thing is that if you begin with uncorrelated photons, this quasi-classical state we call coherent, use Poisson statistics, as you said, that shift is exactly 1 photon. So if you were a classicist physicist, one who said, I don't want to think about things quantum mechanically, you would tell me your experiment did not prove anything about 1 photon. All you did is you measured how much noise your source had. And by a funny coincidence, your result turned out to be 1 quantum vacuum unit. Right? That's the coincidence built into Janes' theory, that is the right unit of noise. But that would be a perfectly reasonable way of thinking about it. So here's the picture we took. This is the semi-classical, or classical in this case, view of an interferometer. I send in a field E0. Each arm has an identical field E0 over 2. They interfere over here, and we get some intensity out the output ports. What is the simplest extension of this to include fluctuations? We didn't want to go whole hog. We wanted to do the simplest thing that reproduces the essential elements. So we let just this field, the one that we're being measured, fluctuate. So what if E1 is on average E0 upon 2, but has some additional fluctuations? Now, when this detector fires, I can figure out which values of E1 were more likely to cause that detector to fire, and update my probability distribution and conclude the average value of E1 when this fires is slightly different. And let's see how different. And if we imagine that we're making a measurement of it, that's what my atoms are supposed to be doing, then that'll tell us something about what happened. Well, the probability of a click grows quadratically with this electric field. In particular, there's some region, if you look at this green curve, where there's perfect destructive interference. And if you're detuned slightly from that perfect destructive interference, you see that you have this quadratic growth here. The initial distribution of the electric field is drawn in blue, this probability of E1. And when you multiply a Gaussian by a quadratic, to lowest order at least, it shifts to the right. So we end up with this red curve, where the most likely value, and in fact the average value of the electric field, is now larger than it was before the click. And the size of the shift, this is what wasn't immediately obvious, we had to do the calculation, is exactly what you would expect given the weak value. So if you really believe that the field strength is an element of reality, and when I say I put in 1 photon or I send in a coherent state, I'm only giving you a probability distribution about that deeper underlying reality. And then you said, well, when the detector clicks, I'm learning something else about the ontic state. What would you expect to happen if you did a measurement, like my nonlinearity, that's proportional to the square of this field, the number of photons? You would expect exactly the thing that we saw in our experiment. Well, no, you wouldn't. I did make one approximation there. It turns out that works when the coherent state is very intense. And we calculated it and then simulated it for weaker and weaker coherent states and smaller deltas. And what you see here is the weak value prediction that diverges as 1 over delta, this deviation from the completely dark interferometer. And the neoclassical calculations for different input coherent states. And they all agree out at large delta, or they agree for large alpha intense coherent states. But for each coherent state, there's a point down here where delta is just too small. And if you get that close to an impossible post-selection, you no longer get agreement with the weak value prediction. Many of you may realize even experimentally weak values, if you make delta too small, deviate from the ideal case. But that's because of the back action of the measurement. And I want to stress that's completely different from what I'm showing you here, because there is no back action in this case. I'm asking, what is the actual probability distribution? What is the peak of that P modified of E1? We haven't modeled the measurement. We're just imagining that there's a measurement really looking at it. So this is very different over here. And here's the either depressing or exciting part. Shown with error bars are the data from our original experiment. And although they agree with the weak value prediction, they also agree with the neoclassical prediction, because we didn't know that there was this other model that would then diverge. So some people see that as depressing. We didn't do the right experiment, but as an experimentalist, I see it the other way around. That means we have to do another experiment. So we need to repeat this. And oops. I think the moral of the story is that something like these Jaynesian elements of reality could underlie our weak value observations and explain why do we see that sort of thing. That model isn't complete. It does not completely agree with the weak value predictions. But it's certainly compelling that it sometimes agrees. You know, I wouldn't want to be in the situation of saying, oh, when you have a lot of classical noise, then your weak value prediction is just telling you about the Bayesian update rule and how on the occasions that the detector fires, you really had something more intense. But then smoothly, as you turn the intensity down or turn down the amount of noise, the result remains the same, but that explanation starts to fail. And the same formula is now true, but it must be for a different reason. Right? I prefer to see some way to connect those different regimes. And I think that's what we should be groping towards now. Right? So that's where we stand on this experiment of counting one photon and seeing a result of 1,000. We're setting up revised versions of that. But I want to tell you, how much time do I have left, Howard? Good. Then I'll actually have time to tell you about these things. A few different experiments on quantum ontology, so to speak, that are ongoing. One of them is coming back to these Bohmian trajectories, but in momentum and in real space. One of them about this pigeonhole paradox, and more about these seemingly negative probabilities and so forth. And one of them is our long-standing experiment on atom tunneling times. And beginning to think that we're going to have to come around and do weak measurement of the Bohmian trajectories of the tunneling particles. That wasn't something I took very seriously until the discussion a few months ago got me thinking we're really going to have no option but to do that. It just fits too well into our portfolio, so to speak. So here's part one. You've already seen this picture thanks to Basil. The idea was to build a kind of two-slit interferometer for photons. These photons were combined at a prism to make two virtual slits. They propagate along to a screen, a CCD camera, where we can study the interference pattern. But along the way, we weakly measured their polarization. We did that using a birefringent material, a crystal of calcite. And then at the end, in addition to looking at the interference pattern, we were able to read out that polarization rotation so that at each position in a given plane, we could tell what is the weak value of the momentum for particles reaching that position. And that's how we reconstruct trajectories. So I can't resist showing you this old movie. It's not very high quality, but I never tire of looking at it. This is actually a series of pictures of what we got on that CCD camera. So what you see now is on the left one spot, on the right one spot. You're going to tell me that I need new glasses. There are two spots. But the horizontal dimension is the important one in our case. The vertical dimension is separating out the two polarizations. So what really happens is that the very slight difference between the intensity here and the intensity here, you don't even see by eye, that tells us the weak value of the momentum. And as I let this propagate, you'll see these spots begin to diverge, so they overlap and form an interference pattern. And down here, we'll track in each of these planes what happens to the weak value of momentum as a function of position. So they're not overlapping yet. Oops, they're beginning to interfere, weird things happening to the momentum. And since in each propagation plane we know momentum versus position, weak valued momentum, we can build up these ugly trajectories. They're a little less ugly in the actual published data. They're not perfect, but that was the basic demonstration that we could measure something that corresponded to the weak value of these trajectories. Well, the question that John Sipe came up to me with is why concentrate on trajectories in position space? The original formulation of Bohm's theory singled out position as the correct ontological variable. But you can construct a Bohmian theory with momentum, let's say, as the ontological variable instead, and ask what would happen there. And we thought it would be interesting to be able to do similar measurements, but either do momentum post-selected on position, or position post-selected on momentum, or momentum at one time post-selected on momentum at a slightly later time, and find out what was going on. So here's the idea of the experiment. It begins the same way, but there are a bunch more optics, and in fact, I think these are no longer considered the correct optics. That's what we're working on right now, that allow us to change whether we make position or momentum measurements in each of the relevant planes. That's what it currently looks like in the laboratory. Two beams from fibers that have already been split come down. They're combined over here, and they propagate down that line of optics. May or may not be able to see that well. And here are the predictions. The blue trajectories are the familiar ones for the position of a Bohmian particle propagating. And the, whatever that is, rust-colored ones are telling us something about what the position would be doing in a momentum space Bohmian picture. I don't know how seriously you want to take that. There are different ways you can think about these pictures. But the basic idea is if you follow trajectories in momentum space, well, in free space, momentum is conserved, and that doesn't change in the Bohmian picture. So it turns out that the momentum space trajectories are you begin with an interference pattern, and it stays there forever. And in fact, the correlation between position and momentum becomes one-to-one, as you see by these straight lines in this case. The way John Sipe likes to argue this is that to see a different flavor of Bohmian theory reconstruct trajectories just as well would imply that, in his words, if everybody is somebody, nobody's anybody. If there's no unique theory, then it's difficult to put too much reality to any one of these ontological interpretations. Now, all of these experiments actually go back to a proposal of Howard Wiseman's in this paper over here that addressed that very point and showed that although you could use these weak measurements to reconstruct trajectories in position, for instance, if you did it in position, they would agree with the Bohmian trajectories, and that would not necessarily be true in, for momentum. Turns out in particular, there's something special about position, which is that it's conjugate to momentum, which only appears quadratically in the Hamiltonian. Momentum, of course, is conjugate to position, which doesn't need to appear only quadratically in the Hamiltonian. It could appear to higher order, and there this breaks down for p. So that's a future experiment we'd like to get to. My student's been doing some simulations. This compares the weak measurement trajectories with what you just expect from the continuity equation or from Bohmian mechanics. This is for the position of a Gaussian wave function that's breathing in a quartic potential. And if he repeats this in momentum space, you see that the red and blue no longer agree. So that's a first step towards figuring out what experiment we can do that really shows that you don't get the same kind of agreement. Here's another example. Some of you have heard about this pigeonhole paradox. The pigeonhole principle, for those of you who don't know it, is just that if you have 3 pigeons and 2 boxes, there are going to have to be at least 2 pigeons in one box. That seems pretty incontrovertible. The fascinating thing is that, like so much else, when you think about it in a post-selected sense, quantum mechanically, those pigeons don't like me. Maybe one of them was sitting on the cable. If you prepare the pigeons in this particular state and you post-select them in this state, you find out that no 2 pigeons are ever found in the same box. And I put that in quotation marks because this presupposes that you do a measurement of whether or not they're in the same box, not which box they're in. If you do it that way, then this turns out to be true whether you do the measurement weakly or strongly, kind of as in that 3-box case. But it raises a lot of interesting questions. And this experiment's been carried out, but I'm more interested in thinking what it will let us elucidate about the nature of these different post-selected measurements. And here's a plot that tries to indicate what's going on as we go from weak measurements to very strong measurements. And we ask, are both pigeons in box 0? Are both pigeons in box 1? Or just are both pigeons in the same box? We get answers that follow the following thing. For strong measurements, the context matters. When I choose what to measure, that disturbs the system. So I may get one answer for A if I measure A and expect a different answer if I'd been measuring something else. In other words, the probability that they're both in 0 or both in 1 doesn't have to be the probability that they're both in 0 plus the probability that they're both in 1. Those are different measurements I may not be able to do simultaneously. Weak measurements, however, don't disturb the system, so they're context independent. The probability of them both being in the same box must be the sum of them being in these different boxes. So how do we get the sum of these two things to be equal to 0? The answer is that for weak measurements, these individual probabilities, the weak values of the projection operators, didn't have to be non-negative. They could have been negative, they could even have been imaginary in this case. But their sum is guaranteed to be 0 over here. For strong measurements, on the other hand, you always get something within the eigenvalue spectrum of the operator. You always get something between 0 and 1 for a projection operator, but the sum rule breaks down because of the disturbance. So our goal here is to try to build a set of interferometers. 3 of them represent pigeons, and one of them is used for Aaron Brodish's clever scheme for varying the strength of this retroactively. And in each box, the pigeon either goes clockwise or counterclockwise, and we're going to ask, is it possible that no two pigeons are going in the same direction in their little Sagnac interferometers? So that also is in the process of being set up. There are 4 Sagnac interferometers, and we're now working on all of the polarization optics required to do those weak measurements. One last advertisement will be for our tunneling experiment. And those of you who've known me for a long time have heard me talk about this too many times, but we're finally getting really close to doing this. We want to study how long does poor Werner here spend inside the forbidden region as he's tunneling through that wall. And the trick is he's got to hold on to some clock that lets us read off his interaction with the wall after he's transmitted. That's going to be the weak measurement of how long he spends in that barrier. And in practice, we have Bose-condensed rubidium atoms that we send through an optical waveguide colliding with an optical barrier. And we're going to use Raman beams to rotate the spin of those atoms while they're tunneling through and read that out at the end of the day. So there are a lot of different ingredients. My students have spent a lot of time learning how to cool those atoms, so far down to 900 picokelvin. They're still not satisfied. They say 300 and that'll do it, but 900 is just a bit too hot. They've learned how to put the atoms on top of a barrier. You see them starting to leak through the barrier here. They've learned how to connect them to those Raman beams to make a clock. These are the spin states of the F=2 rubidium processing under the influence of those Raman beams. And they've demonstrated that we have coherence between the reflection and the transmission from these barriers by building a Fabry-Perot cavity. The picture you're seeing here is atoms being trapped in a basically micron-wide cavity as one quantum wave. So hopefully with all these elements, we'll soon be able to carry out the actual measurement of those tunneling times. Let me just leave you with this basic conclusion. If there is some deeper reality underlying quantum mechanics, then I think that these weak measurements, so the post-selected behavior of systems, must be telling us something about it, and we should keep investigating what that is. And I'll leave the other conclusions for you to read, and just thank you for your attention.